Okay, this is Unit 6, Lesson 1, Key Features of Exponential Functions. So our lesson essential question is, how do graphs and equations reveal key features of exponential growth and decay functions? At the end of this lesson, you'll be able to recognize the key features of exponential functions. Example 1, identify key features of exponential functions. What are the key features of the function? Include domain, range, intercepts, asymptotes, and end behavior. So f of x equals 2 to the x power. So I use the graph to explore the key features of the function. So here's the graph below. An exponential function is any function of the form y equals a times b to the x power, where a and b are constants, with a not equal to 0, and b is greater than 0, and b can't be 1. For f, b equals 2, since b is greater than 1. The y values of the function increase. For y equals a times b to the x, the value of a is the y-intercept. My domain is all real numbers. My range is y, where y is greater than 0. I have a y-intercept at 1. I have an asymptote on the x-axis, and my end behavior as x approaches negative infinity, y approaches 0, and as x approaches infinity, y approaches infinity. So as I go this way, I get closer and closer to 0, and as I go this way, I get higher towards infinity. All right, what are the key features of the function? Include domain, range, intercepts, asymptotes, and end behavior. G of x equals 5 times 1/2 to the x power. So for g, b equals 1/2. Since b is greater than 1, the y values of the function decrease. My domain is still all real numbers, so all my x values. My range is still y is greater than 0. My y-intercept, according to my graph, is at 5. My asymptote is still the x-axis. And my end behavior as x approaches negative infinity. So as I'm going this way, my x values get larger. They go toward infinity. My y values get larger. They go toward infinity. Okay. And as x approaches infinity, so I'm going this way, my y values approach 0. All right, so let's try it. Graph f of x equals 4 times 0.5 to the x using the tool at the right. Then answer the questions below. So 4 tells me where I cross. So there's 4. And I'm getting closer and closer to 0. So my asymptote is still here at x equals 0. So my domain is all real numbers. My range is still y, where y is greater than 0. My intercept, I have a y-intercept at 4. I have an asymptote on the x-axis, and my end behavior as x approaches negative infinity, y. So as x approaches negative infinity, y approaches infinity. And then as x approaches infinity, y approaches 0. Example 2, graph transformations of exponential functions. Graph the function, describe the graph in terms of transformations of the parent function f of x equals 3 to the x. How do the asymptotes and intercept of the given function compare to the asymptote and intercept of the parent function? So g of x equals negative 3 to the x power, so I have a negative. Okay, so I use the slider to set a equals -1. Okay, so there's my slider. So I can see the blue is my 3 to the x power, so g of x equals a b to the x plus a. A is -1. Right, because remember we did -3 to the x. So -1, you can see it flips a function over the x-axis. So it's a reflection. When the sign of a changes, the function is reflected across the x-axis. Okay. So g of x equals negative 3 to the x equals negative f of x. The intercept changes from a to negative a. The asymptote of the function does not change. It is still the x-axis. So I graph the function, describe the graph in terms of transformations of the parent function f of x equals 3 to the x. How do the asymptotes and intercepts of the given function compare to the asymptote and intercepts of the parent function? Intercept. Okay, so b is h of x equals 3 to the x minus 4. I have no value out here for a. Okay, so nothing changes for a, so it's going to stay like this. Okay? But I do change my value of k. Now notice what happens when I change my value of k. I'm going up or I'm going down. Okay. So in this case, I'm going down to minus 4. So this, when adding a constant k, the function shifts vertically by k units. So it goes down to negative 4. So now my asymptote is at k equals negative 4. So the intercept changes from 1 to 1 plus k. The asymptote of the function also changes. So it is y equals k or y equals negative 4. All right, so let's try it. How do the asymptote and intercept of the given function compare to the asymptote and intercept of the function f of x equals 5 to the x power? So I have g of x equals 5 to the x plus 3. Okay, so this plus 3 is up here in my x. Okay, so that's going to tell me that the asymptote doesn't change. So the x-axis for both functions. The y-intercept, though, is translated. So the y-intercept is translated from 5 up to 125. So if x were 0, 5 cubed gives me 125. Okay. For b, h of x equals 5 to the negative x. Okay, so this one, the asymptote and intercept are the same for both functions. All right, example 3, model with exponential functions. So the population of a large city was about 4.6 million in the year 2010 and grew at a rate of 1.3% for the next 4 years. What exponential function models the population of the city over that 4-year period? Okay. So I compute the population for the first few years to look for a pattern. So in year 0, I have 4.6, right? Okay. Year 1, which would have been 2011, are 4.6 million people, and then another 1.3% of the 4.6 million are added. So 4.6 times 0.013 plus that 4.6 gives me this amount. Okay. So that value, just in case you're curious, is 4.6598 million. So it doesn't increase by that much. Year 2, I take that amount, that 4.6 times 0 times 1.013 times 1.013, or 1.013 squared. Okay, so I'm taking 100%, which is that 4.6 plus that 0.013. That's what this represents. Okay. And then I repeat that process. You can start to see that year 2, so this, the exponent is representing my years. The 4.6 is where I started. So for 3, it would be 4.6 times 1.013 cubed. So that's that 0.013 increase. For 4 years, it would be to the 4th. So the exponent of the number of years since 2010. So my function model is going to be the population after t years. So P, my population in 2010, which is where I started, my growth factor of 1.013 to the t power, which is the year since 2010. So the population of a large city was about 4.6 million in the year 2010, and grew at a rate of 1.3% for the next 4 years. So if the population continues to grow at the same rate, what will the population be in 2040? Okay, so the first thing that I need to do is I can see, here's my pattern. Okay, I need to figure out how many years. So to find the population in 2040, I solve the equation for t. Okay, so t equals 30. And I got that from 2040 minus 2010. So it's been 30 years since the original. Okay. So that's where I got t equals 30 from. And then I just substitute that value in for t. So 4.6 times 1.013 to the 30th power is approximately 6.78. So in 2040, the population will be about 6.78 million people. All right, so let's try it. A factory purchased a 3D printer in 2010. The value of the printer is modeled by the function f of x equals 30 times 0.93 to the x power, where x is the number of years since 2010. What is the value of the printer after 10 years? So they told me 10 years, so that's my t, my x value. Okay, so I'm going to substitute that in. So f of x equals 30 times 0.93 to the 10th power. So when I put this into my calculator, so here's my calculator, right? So I'm actually going to enter it in. So let's see, it's 30. So notice I have 30. And then I opened a parentheses. So I'm going to type it in exactly how it's written. So 30 times 0.93. I'm going to use the little caret feature to the 10th. Okay. And then I just come down here and hit the enter button, and it gives me my answer. So f of x equals 14.51946922. Okay, obviously I don't need all of that information. Okay, so I'm going to use what I need. This printer, so if it purchased this, the value of that printer, so this is going to be money. So money is usually the 2 decimals, so it'll be about $14.52 because 519 I round to 2, so $14.52. So does the printer lose more of its value in the first 10 years or in the second 10 years after it was purchased? Okay, in order to figure out the second 10 years, I do the same thing. So f of x equals 30 times 0.93 raised to the 20th power. So in the second 10 years, it's going to lose $7.03. So this would be the first 10 years. Okay. In the first 10 years, it lost $14.52. In the second 10 years, it lost $7.03. All right, so concept, exponential growth and decay models. Exponential growth and exponential decay functions model quantities that increase or decrease by a fixed percent during each time period. Given an initial amount, A, and the rate of increase or decrease, R, the amount A of t after t time periods is given by an exponential growth model, so 1 plus R, or an exponential decay model, 1 minus R. In this case, B, remember on our original A times B to the x power, B equals 1 plus that value, or B equals 1 minus that value. The growth or decay factor is equal to B and is the ratio between 2 consecutive y values. All right, example 4, a car was purchased for $24,000. The function y equals 24 times 0.8x can be used to model the value of the car in thousands of dollars, x years after it was purchased. Okay, so first, I'm looking at 0.8. 0.8 is less than 1, so this is going to be a decay model. Okay, so does the function represent exponential growth or decay? Well, 0.8, again, is less than 1, so the function represents an exponential decay. So what is the rate of decay for this function? What does it mean? So b equals 1 minus r. B is 0.8 equals 1 minus r. I solve for r, which gives me 0.2. So the rate of decay is 0.2 or about 20% every year. So every year, the value of my car is going to decrease by 20%. Okay, so this is actually real life. When you buy a car, it's not worth what you bought it for after you've used it. Okay, it goes down every year. Okay, the more miles you put on it, this decay often gets larger. Accidents also are included in that decay. So that's where this kind of function starts to come from, is the amount of miles that's expected to be put on the car with possible accidents, things like that, okay? So I'm taking 1 because it's a decay, 1 minus that value to figure out what the 0.8 represents. So C, I want to graph the function on a reasonable domain. What do the y-intercept and asymptote represent? When will the value of the car be? About $5,000. Okay. So I go ahead and graph this function on my calculator, my handy dandy calculator. I find the value of x when y equals 5. You can use Desmos, by the way, to do this. The graph approximately passes through the point 7, 5. This means that the value of the car will be about $5,000 after 7 years. All right, so let's try it. 220 hawks were released into a region in 2016. The function f of x equals 220 times 1.05 to the x can be used to model the function of hawks in the region x years after 2016. Is the population increasing or decreasing? Explain. Okay. So first, looking at this, I have 1.05. So that means it's an increase. Okay. So it's increasing. The base is greater than 1. So the function increases as x increases. Okay. So let me go ahead and graph this. F of x equals 220 times 1.05 to the x power. Okay, so here's my function. I want to graph the function on a reasonable domain. In what year will the number of hawks reach 280? Okay, so I'm going to come up here, look for 250, 70. All right, so here's 280, it's 4.97, so roughly 5. So after 5 years, hawks will reach 280 after 5 years. The first year was 2016, so 2016 plus 5 gets me to about 2021, so it would be around 2021, probably near the beginning of the year or at the end of 2020. Okay. So here we saw 4.9. Okay, so it's really close to 5 years. So years after 2016. So 4 years after 2016 is 2020, and it'll be at the very end of 2020 or right at the beginning of 2021. Example 5, compare two exponential functions. A museum purchased a painting and a sculpture in the same year. Their changing values are modeled as shown. Find the average rate of change of the value of each artwork over the 5-year period. Which artwork's value is increasing more quickly? So sculpture's value is f of x equals 50 times 1.075 to the x power. So value in thousands of dollars in x years. Okay, so this is my f of x will be the value in thousands of dollars in however many years for the x. Okay, so here's my value in thousands of dollars for my painting. So I started at 40,000, and after 5 years, it's 64.4 thousand. So at 0, it's worth 50,000 because anything to the 0 power is 1. And then on the 5th year, because that's what it asked for 5 years, it's 71,000.78. Okay, then I subtract the rate, find the rate of change or the slope. So 71.78 minus 50 over 5 minus 0, that's the year change in years, which gives me 21.78 over 5 or 4.356. So it changes about $4,000, a little over $4,000 every year. Okay, same thing for my painting value. They didn't give me the function, but they actually gave me the 2 points. So I use those 2 points. I subtract my y values divided by my subtracted x values. So I get 24.4 over 5, which equals 4.88. Okay, so the sculpture's value increased at an average of $4,356 per year, while the painting's value increased at an average of $4,880 per year. So over the 5-year period, the value of the painting increased at a greater average rate than the value of the sculpture. All right, so let's try it. A museum purchased a painting and a sculpture in the same year. Their changing values are modeled as shown. Will the value of the painting ever surpass the value of the sculpture according to models? Okay, so here's my sculpture. Here's my painting value. So yes, the value of the painting will surpass the value of the sculpture. Okay, so yes, the value of the painting is increasing at a greater average rate than the value of the sculpture. So the painting will eventually be more valuable. All right, concept summary, key features of exponential functions. So my exponential growth, remember I'm adding that growth factor of 1 plus whatever my factor is. Exponential decay is 1 minus that factor. So my equation's y equals a times b to the x power for anything that's b greater than 1, and my decay is for anything between 0 and 1. Okay, you can't have anything, you can't have a negative number when you're dealing with exponential decay. So my domain for my exponential growth is all real numbers. My range is for y greater than 0. My intercepts are 0, a. My asymptote's usually the x-axis. Same thing for decay. My end behavior looks relatively similar. For growth, it's going to be as x approaches negative infinity, y approaches 0. So looking at the graph, I approach 0. As I approach positive infinity, I'm going to get larger y values as well. It's the opposite for exponential decay. So as I'm approaching negative infinity, I'm going towards positive infinity. As I'm approaching positive infinity, I'm getting closer to 0. Okay. So growth is a of t equals a times 1 plus r to the t power. Remember, t is years usually. Same thing with decay, except instead of a plus, you have a minus. And that is the end of Unit 6, Lesson 1.